Moving on in chapter 7 today, we're going to start seeing a shift in the way we do problems. Up till now, to chapter 7, we've been doing data, and I mentioned this the last time we were together. We were doing data as, the Shy Sam problems. What's the probability a girl is taller than Shy Sam? What's the probability that a person has an IQ of 120? That's the way we were doing problems so far. And we found out in our last time together that it is a much better way of doing sampling for industries and business if you look at sample means, if you look at the mean of a group of products, instead of just picking out one product to examine and see if it meets the criteria, it's much better and fairer to pick out a sample of products and see if their mean meets the criteria. Okay, so that's where we're headed today, just kind of a preview of coming attractions. All right. So before we get in there, we got to have a interesting statistic today, a surprising stat. Recently, school choice came to the Chicago public school system. Some interesting things about Chicago public school system. It's the third largest in the country with more than 60 high schools. 60 high schools. Half of the Chicago public school students opted to choose another school. Okay, they had a chance to choose. There were so many students who wanted to change schools that they had to use a lottery. Wow, what more do you want? Random sampling, there's a lottery. That's perfect, okay? And there were a couple of interesting conclusions that we found from this study, okay? Students who attempted to opt out of their neighborhood school were more likely to graduate. Okay, who attempted to leave their school. Remember, it was a lottery. Who attempted to leave their school meant those students and their parents were probably more motivated. The amazing thing was whether or not they actually moved really did not mean anything. They still did better. I just find that to be so incredibly interesting. It wasn't the move. It wasn't the move. The kids that didn't move, they continued to test about the same levels as before. Had they wanted to move, they'd have been successful, more successful than the others who didn't want to move and continued to test at the same level. The kids who tried to move, some won the chance to move, some lost and stayed in the same school. But both groups were more likely to graduate than the kids with no interest in moving. Attitude is huge. Attitude is huge. Isn't that cool? Okay. It wasn't the move, it was the motivation possessed by the groups. What a great stat. There was one group that did prosper from moving. It was students, obviously, who opted for a tech school. Here they had specific training for specific trades, and it made a huge difference, okay, for a tech school. And that stands to reason. But the other one is just so interesting. Okay. Let's go back to what we were talking about the last time we were together, okay? We are going to consider the data 4, 9, 11, and 12, just 4 items to make it really, really simple. Find the mean for this set. All right, so we have 20 here, we have 16 here, that's 36 divided by 4 is 9. The mean for the set of data is 9. Now we want to find sample means for all samples of all possible sizes. But remember, before we go any further, where's my marker? Before we go any further, we know that mu is 9 for the population. Okay, now samples of size 4. All right, samples of size 4, there's only one of them, okay? And the mean is 9. We already figured that out. This is the same as the population. So the mean of the sample means, you just have one sample mean, 9. What's the mean of 9? You add up 9 and divide by 1. There's one of them. It's 9, okay? So the mean of samples of size 4 of all the sample means is 9. Now make sure you get what we're doing here. We are finding the mean of the sample means. We are considering the sample means as a set of data, okay? That's what is the most confusing thing about what we're doing here, all right? We're considering sample means as a set of data. There is one item of data here. The sample mean is 9, okay? Maybe as the phrase goes, beating a dead horse here. But the sample mean is 9. And what is the mean of 9? It's 9. All right, let's go to samples of size 3. Okay, here they all are. I wrote them out, 4, 9, 11, 4, 9, 12, 4, 11, 12, 9, 11, 12. I found the mean of each one. You know, I have to add 4, 9, and 11 and divide by 3. So that's 13, 11 is 24 divided by 3 is 8, see? Okay, so I'm finding the mean of each one. I did that ahead of time just to save us work. Here they are, 8, 8.339, 10.67. That's our new set of data now. There's 4 items of data here, okay? That's our set of data. What is the mean of those sample means? So I have to add up 8 plus 8.33 plus 9 plus 10.67 equals, divided by 4 equals 9. The same as this one, the same as the population. Wasn't that freaky? Okay. Samples of size 2. Samples of size 2, here they all are, 4, 9, 4, 11, 4, 12, 9, 11, 9, 12, 11, 12. You got to add these up, and you get 13 divided by 2, 6.5. You get 15 divided by 2, 7.5, so on. I've added up and divided by 2 for all of those, and here are your 6 sample means. That's a new set of data, okay? Let's find the mean of those 6. So almost do that in my head. 6.5, 7.5 is 14. 14 and 18 is 32. 10.5 and 11.5 is 22. And 42 is, can't do it in my head. 6.5 and 7.5 is 14, darn it. Plus 18 plus 10.5 and 11.5. Is 22, isn't it? Yeah, 54 and divide by 6, and you get 9 again. So the mean of these sample means is 9. Wow. Finally, samples of size 1. You have 4 of them. You have a 4, you have a 9, you have 11, you have a 12. What are the sample means? A 4, a 9, 11, and a 12. And what's the mean of those 4? We already know that. It's 9. Now here is one of the most amazing things of all. When you're finding samples of all possible sizes, if you take then the means of all the samples and you find the mean of the sample means, okay, it will always be the population mean, okay? Always, always, always. This should back up what we talked about on page 300. If you want to turn there, you see what I'm talking about once again. Page 300, that inverted pyramid. Even though you've got green dots all over the place, okay? If you find the mean of those sample means, all those green dots, always going to be in the center in the population, and same as the population. It is a really cool result. One less thing for you to have to worry about, because the mean of sample means is always the same as the population mean. Now, what about the standard deviation? What about the standard deviation? If you go back to page 300, you can see from that inverted pyramid, because some of them have more spread, right? We know that it gets more accurate as the number in each sample gets bigger and bigger and bigger, okay? Like for instance, as we went from 1 to 2 to 3 to 4, okay? We got more accurate because they got closer and closer. The means here were 4, 9, 11, and 12. They're all spread out all over everywhere. The mean up here is just 9. Boom, it's centered right on the population mean, okay? There's a variety of spread here, as the green dots show on page 300. So we know that the standard deviation is not the same, okay? We know that. All right. So how do we find standard deviation? Before we get there, just a little bit of notation. The mean of the sample means is mu of x bar, okay? We know that mu of x bar is always equal to the population mean. But what about the standard deviation? Okay? Now, remember standard deviations. There's two formulas if you do a population or if you do a sample. Two formulas, if you do a population, you divide by n. If you're doing a sample, you divide by n minus 1, okay, before you take the square root. Yeah? Yeah? Now, here's what's a little tricky for what we're going to be doing right now. Because whenever we're looking at sample means, we're looking at all the sample means for one size, how many items, okay, samples of size 2, for instance. We're going to take all the sample means, so that's a population. So we're going to be using the population standard deviation. All right, so let's go back to 4, 9, 11, and 12. We know that mu is equal to 9. Okay, we want to calculate the standard deviation of the sample mean. So if we do samples of size 4, okay, samples of size 4, there is only one of those. Therefore, there is only one sample mean, right? And we found it was 9, okay? So if the sample mean is 9, okay, and the population mean is 9, all right, what is the standard deviation? Okay, they're 9 and 9, they're right on top of each other. Okay, so the standard deviation for this one, standard deviation of the x bar here is 0. Okay, for samples of size 4. Okay, and that makes sense because we can have samples of size 1, 2, 3, or 4, and we know that as your sample size goes up, the inverted pyramid, it clusters more tightly around the mean. And doesn't it make sense if your sample size is 4, you'd have no standard deviation at all. It's centered right on that mean. Okay, let's go to samples of size 3. All right. The sample means are, and I'm going to work this one out with a chart. Okay, let's work this one out. If you remember the chart we did, you put all your data. Okay, so my data are the sample means. Remember, it's a new set of data. So I have 8, 8.33, I have 9, and 10.67. This is the data. Okay, then here we put the population mean right here, which we know is 9. And it's the same as the mean of the samples, okay? So we want to subtract and square it. So if I subtract here and square it, I get 1. Squared is 1. If I subtract there, I get 0.67, and squared is, turn the calculator on, 0.67 squared is 0.45. 0 squared is 0. 1.67 squared is 2.79. Okay? These are all the sample means for samples of size 3. That's all of them. It's the total. It's the population. Okay? So I'm going to add those up. So I have 2.79 plus 0.45 plus 1 equals, I'm going to add those up. I'm going to divide by 4, not 1 less. Divide by 4 equals, and I'm going to take the square root of that answer, and I get 1.03. Okay, so the standard deviation for samples of size 3 is 1.03. Okay? Now, for samples of size 2, I'm going to do it on the calculator just to save a little bit of time. Okay? So for samples of size 2, we want data put in here of all the sample means. So I have 6 of them. So I have 6.5. I have 7.5. I have 8. I have 10. I have 10.5. And I have 11.5. Okay? Now, I want to get my population standard deviation. There are 6 items of data. The mean was 9, we knew that, same as the population mean. We don't want the sample standard deviation, we want the population standard deviation, and I get it is 1.78, okay? Finally, samples of size 1 are just 4, 9, 11, and 12, and the 4 sample means are 4, 9, 11, and 12, okay? So I need the standard deviation of 4, 9, 11, and 12, so let's clear the variables and see if I remember how to do this. Okay, so clear out the data. We want to find the standard deviation of 4, 9, 11, and 12. So we have 4, 9, 11, and 12. And we have 4 items of data. We have 9 is the sample means mean, right? And we want the population standard deviation. Now, once again, this bears out perfectly what we've been talking about. Samples of size 1, look at the standard deviation, really spread out. Samples of size 2, smaller standard deviation, it's starting to come in. Samples of size 3 coming in tighter. Samples of size 4, no standard deviation at all. It's 0 because it's centered right on the mean. Okay? Pyramid, right? More accuracy when you increase the sample size. That's this stuff beautiful or what? Now, you can do all kinds of great problems with these. Okay? And we're going to get to the problems in a second. Okay, we talked about this. The standard deviation will decrease as sample size increases. Is there a way to find the standard deviation of your sample means without going through the chart or on a calculator like I just did? Yes, there is. The easiest way is to simply take the population standard deviation and divide by the square root of the sample size. I'll say that again. The easiest way to find the standard deviation of the sample means is to take the population standard deviation and divide by the square root of the sample size. All right? That is going to mean when you, and I will say this 20 times over the next couple of class periods. When you are doing Z problems, remember, if you would, X minus mu all over sigma, right? But if you're working with sample means, okay, the mu stays the same as the population. That's easy, okay? But this becomes this. Okay? You got to really be careful of that, okay? You've got to divide by the square root of n if and only if you're dealing with sample means, darn it. All right, so make that huge distinction here in the gray matter and also in your notes. If the problem talks about sample means, you got to divide the population standard deviation by the square root of n, okay? Now, back in this problem, we just went through all of that, finding standard deviations. I want to really highlight this. I went through the standard deviations using the chart. If you divide by the square root of 3, the square root of 2, square root of 1, the shortcut way that I just mentioned, your answers are going to come out slightly differently than what I did because we only had 4 items of data. I wanted to keep it simple, okay, so that it wouldn't take us forever to work these out. But the formula you need is when you're working with means, the standard deviation is the population standard deviation divided by the square root of n. Okay. All right. Problems. If the mean living space of single-family dwellings is 1742, standard deviation of 568, okay, there's the population mean, 1742. Standard deviation of 568 is the population standard deviation. For samples of size 25 homes, find the mean of the, and standard deviation of the sample means. Okay, now we know the mean for samples of size 25 is the same as the population mean. So the mean right here the mean is still 1742, okay? But the standard deviation for samples of size 25, you have to take 568 and divide by, okay? Standard deviation of means is the population standard deviation divided by the square root of n. I've got to take 568 and divide by the square root of 25, which is just 5, and I get the mean of the standard deviation of the sample means is 113.6, okay? 113.6. How about samples of size 100? Doesn't matter. The mean, population mean stays the same for samples of size 100, 1742, okay? Standard deviation for samples of size 100, okay, is simply 568 divided by the square root of 100, which is 568 divided by 10, which is 56.8, okay? This one, the standard deviation is 56.8, and what did I say the standard deviation was for that one? 113.6. Look what happens. When your sample size gets bigger, look how the standard deviation decreases, becomes more accurate, right? More accurate. Okay. How much variation would you expect for samples of size 100? Okay. Remember, we have a normal curve, okay? We know that mu 1742. We know that 99.74% of the data is between plus or minus 3 standard deviations. What was the standard deviation for samples of size 100? Didn't we divide by 10? Wasn't it 56.8? Yeah? So don't I need 3 of those added on to that? So it's 1742 plus 3 times 56.8, which is 1912.4. And it's 1742 minus 3 times 56.8 is 1571.6. So how much variation? From 1571.6 to 1912.4. Okay? We knew that already. 3 standard deviations above and below. All right, let's go down to this one. For 6, 9, 11, and 15, find a standard deviation first before we go. Let's just stop right there. Let's find a standard deviation for 6, 9, 11, and 15. Once again, to save time, I'm just going to punch it into a calculator. Okay, so let's clear out the data first. Okay, so my data is 6, 9, 11, and 15. And once again, if anybody has any trouble doing this, okay, on your calculator, please talk to me and I'll explain your calculator and how you can do it. Okay, so there's 4 items of data. The mean of this is 10.25. I'm going to jot that down right away before I forget it. Add them up and divide by 4, which is what the calculator just did. And the population standard deviation is 3.27. Okay? All right. Now, find the standard deviation of the sample means for samples of size 3. Oh. Samples of size 3, I must take 3.27 divided by the square root of 3, and I get, I'm going to do that again. 3.27 divided by is 1.89. So for samples of size 3, the standard deviation is 1.89. Okay? Now, this kind of integrates what we're about to do next, integrates everything we did in chapter 3 and chapter 6. Okay? Look at this. Determine the percentage of samples of still size 3 within 1 of the population mean. In other words, let's go back. Here we are, 10.25, right? If you're within 1 of the population mean, aren't you at 11.25 and 9.25? Yeah? So what is that in between? Okay, what is that? Well, I'm going to have to do a z-score. It's going to have to be, I'll find first the z-value for 11.25 minus 10.25 all over the standard deviation for samples of size 3, darn it, is 1.89. And then I'll do 9.25 minus 10.25 all over 1.89. Okay, right? And by the way, isn't that positive 1 and that's negative 1? So it's plus or minus 1 on the top. So it's 1 divided by 1.89. I get 0.53 for a z-value and negative 0.53. So look them up on your chart. On your z chart, I'm going to look up 0.53. 0.53 is 0.7019. So from here down, the area is 0.7019. Negative 0.53 is 0.2981. So from here down is 0.2981. How do you find the area in the middle? We've done this countless times. You simply subtract 0.7019 minus 0.2981 equals, and it's 0.4038 or 40.38%. Okay? Samples of size 3 would have a mean within one of the population mean, between 9.25 and 10.25. Is that cool or what? All right? Determine the percentage of samples of size 2 that would have means less than 9. Whoa! Samples of size 2. Okay, so we got to start over. Okay, population mean and mean of the sample stays the same. All right, so here we are. Once again, samples of size 2, 10.25. We want to know what percentage of samples of size 2 would have means less than 9. Here's 9, right? There's 9. We want to find this. So isn't it 9 minus 10.25 all over the standard deviation? And now I forgot what that was. Curses. Somebody's going to help me. It was. I'll have to do it again, darn it. I forgot what that was and I erased it. Okay, so let's do it. Clear the data. Gun it. Okay, 6, 9, 11, and 15. So data is 6, 9, 11, 15. Thank goodness for calculators. All right, so 3.27. Darn it, why couldn't I remember that? Okay, so the standard deviation is 3.27 divided by the square root of 2 this time. Okay? Samples of size 2. All right, means less than 9. All right, do the work. It's negative 1.25 on the top. Negative 1.25 divided by parentheses 3.27 divided by the square root of 2. Close your parentheses, and I get negative 0.54. Look it up in your chart, and since it's to the left, it's easy. Negative 0.54 is 29.46. 29.46% of the samples of size 2 would have a mean less than 9. Determine the percentage of samples of size 2 that would have means greater than 11. Over here is 11. We want to find this. The only change we're going to make in this calculation is to put 11 here. Yeah? Okay? Let's do it. 11 minus 10.25 is 0.75 divided by parentheses 3.27 divided by the square root of 2. Close your parentheses. I get 0.32. Look it up in your chart. I said 32. Why did I put a number? Okay, 0.32. All right, look it up in the chart. 0.32 is 0.6255. But hold everything. 0.6255. That gives us the area to the left. We want the area to the right. Got to subtract that from 1. So 1 minus 0.6255, and I get 0.3745, or 37.45% of samples of that size 2 would have means greater than 11. Okay? This is a little bit new. With all this talk of samples and sample means and dividing by the square root of n when you're dealing with sample means, I understand that this is all a bit new. So it's going to drive you crazy for a day or so until you get into a groove on this. Okay, but technically, everything we're doing is the same with just that little change. When you're dealing with sample means, make sure you divide by the square root of the sample size. Your homework. Book problems, okay? Here's dealing with sample means, right? This is simply a problem back from chapter 6, right? No sample means. You don't have to worry about dividing by the square root of n. This one has 2 kinds of problems in it. One is a sample problem. You're going to have to do that. The other one is not. I'm just testing you to see if you know the difference between the 2. Okay? All right. Make sure you talk to me if you have headaches on this homework.